In the final part of our basic concepts topic, we're going to just have a brief look at reaction mechanisms. We're going to go in far more detail when we look at the different groups as we make our way through the AS chemistry course. But we really just need to have a little bit of an understanding about what reaction mechanisms are. As ever, you can download this resource. You can download the slides by going to my website, chemistrytuition.net. And if you register, it's all for free. And just pop in, just search for organic chemistry resources. You'll see it quite clearly. You'll be able to download this as a PDF. So to understand what we mean by reaction mechanisms, let's have a look at this reaction. We have ethene reacting with bromine to produce 1,2-dibromoethane. You look at this reaction in more detail when you come to do the alkenes, but let's just have a think about how could this reaction actually occur. And really as chemists we're interested in how the electrons are rearranging themselves. So a reaction mechanism will show us a step-by-step process by which the two molecules on my left become the product. So let's have a look at one example and think, is this going to be realistic? So let's have a think about how this reaction may take place. Well, let's just go without knowing anything about reactions mechanisms to think this would be the way that, based on bond making and bond breaking, we assume it takes place. So spontaneously, my double bond here breaks. So that double bond there has gone, so I'm left with a single carbon-carbon bond, and my bromine-bromine bond breaks as well. So what would that leave me with? Well, each electron from my double-double carbon bond would go to each carbon atom, which I've shown here as well. So these dots, red dots, are the two electrons that were in my double bond and have now gone to the carbon atom. So remember, each carbon must have its 4 original electrons in its outer shell. So each carbon, remember, would donate 1 to each of these bonds. So for this carbon here, he's got 1, 2, 3, and that's the 4th one there. And the same for this carbon here. They each will have a lone electron, or we call it an unpaired electron, on the carbon atoms. And we'll also end up with 2 bromine atoms because the bromine-bromine bond has split. And again, in my electrons here that were in this bond, 1 has gone to that bromine and 1's gone to that bromine there. So now each bromine has got 7 electrons in its outermost shell. And we call these species here radicals. And a radical is a species with an unpaired electron. And then what we're going to assume happens is these atoms rearrange themselves and they form new bonds. So this bromine here, the electrons go to that carbon, and this bromine perhaps goes over there to that carbon to form these 2 new bonds here. So let's think about energetically, is that going to be favourable? Well, it's quite unlikely that I'm going to suddenly spontaneously create all those radicals without some sort of energy input. To break a carbon-carbon double bond is not easy. So it will take a lot of energy to do that. It is easier to break a bromine-bromine bond, but it is highly unlikely that spontaneously all those species will be created and then they will rearrange themselves to create 1,2-dibromoethane. So obviously reaction mechanisms is more than just break all the bonds and make the bonds that you want. One thing we obviously can be sure of is that in this reaction mechanism, bonds will be broken. And so to begin this topic, as we learn more about reaction mechanisms, this will be quite useful. There are 2 types of bond fission. One is known as homolytic fission. And in homolytic fission, in my 2 electrons, which are in this hydrogen-hydrogen bond, 1 electron goes to that hydrogen and 1 electron goes to the other hydrogen. So I end up with 2 hydrogen atoms. And because they've got unpaired electrons, I call them two radicals. The alternative is that both electrons go to one atom. Now I'm going to give them to the chlorine atom there. Now you may realise why I'm giving it to those to the chlorine atom from electronegativity. In electronegativity, chlorine is the more electronegative atom in that bond, and so is going to have a stronger hold on the pair of electrons. So effectively, both electrons that were in this bond go to the chlorine here, and therefore hydrogen is left without any electrons, and so is H+. And that is called heterolytic fission. Now, the most important thing in a reaction mechanism is to get your curly arrows right. And a curly arrow describes the movement of an electron pair. So whenever you see one of these curly arrows, it means two electrons are moving, and it's showing heterolytic fission or the formation of a covalent bond. In OCR A-level chemistry, we don't actually show the movement of just one electron. You obviously, as some reactions do involve the movement of just one electron. For example, homolytic fission will. We don't need to describe that, but in a minute I will explain how we do that. So let's have a look at what that would mean. So here I've got my HCl, and I am now going to do a curly arrow to show heterolytic fission. And so what it means is both those electrons on that bond go to that chlorine there, and therefore those electrons are now there on the chlorine ion. So I've got a chloride ion there, and it means that little hydrogen hasn't got any electrons at all, and that is heterolytic fission. An example of heterolytic bond formation is these two electrons on the chloride ion are go towards the H+ ion, and therefore those are those electrons there, and I have now formed a covalent bond through donating those two electrons on the chloride ion to hydrogen. Just in case you are interested in homolytic fission, if I wanted to show that, and an example would be a chlorine molecule, if I want to show homolytic fission, I actually use half headed curly arrows like so, and that would be the correct way of showing the formation of two chlorine atoms or two chlorine radicals. So let's start ourselves off by looking at the interaction between a water molecule, and a hydrogen ion, like so. So I've got a lone pair of electrons on my oxygen atom, so they are likely to be attracted to my H+, because electrons are obviously negative and hydrogen is positive there, my hydrogen ion. So my electrons will travel and form a bond with H+, and those two electrons here are now in this bond here. And I have formed H3O+, by that oxygen forming a bond with H+. So this is the important bit. Curly arrows can start from a lone pair of electrons or a covalent bond, and curly arrows go to atoms or ions which generally lack electron density, so they have delta plus or a positive charge. So let's have a look at using curly arrows in practice. Now you'll be doing lots of examples of these when you come to do the different functional groups and look at their properties, but so we're just going to have a general idea and try and work out how we can use curly arrows, what's likely to happen between a hydroxide ion and bromoethane. So the first thing to notice on bromoethane is that I have a polar bond between the carbon and the bromine, because bromine is more electronegative than carbon, and therefore carbon's delta plus and bromine is delta negative. So along comes my hydroxide, and the hydroxide therefore is going to be attracted to the carbon atom. So my two electrons on the oxygen and the hydroxide are going to be attracted to that carbon there, and so that's my first curly arrow. But carbon can never form 5 bonds, So at the same time that this bond forms is these two electrons go on to the bromine, and bromine will leave as a bromide ion. So what is the result of that? Well, it results in my two red electrons going on to my bromide ion, like so, and my two blue electrons are now between the oxygen and carbon with a new covalent bond. So moving on to the second example, we have got a carbocation. So a carbocation is it contains a carbon with a positive charge, which is here. So this carbon has only got three bonds, and so it obviously it's obviously lost a group somewhere, so it's got a positive charge. And I've also got a chloride ion hanging around. So this is quite straightforward. These lone pair of electrons on my chloride are going to be attracted to my carbon like so, to form a new covalent bond, and so I will end up with this molecule where I have formed a new carbon chlorine bond, which I've shown here with these red electrons there, and that's those two ions have come together. So my final example is ethanoic acid reacting with hydroxide ions. So again, let's have a think about where hydroxide is likely to be attracted. And you may remember that this oxygen is going to be delta negative and hydrogen will be delta positive, if you think back to water and so on. So this hydroxide, this lone pair of electrons on my hydroxide is going to be attracted to my hydrogen there and want to form a bond. But hydrogen can only form one bond. So as that bond forms, these two electrons here will have to leave and go on to my oxygen there. So what's the result? Well, it means that my two red electrons have formed a bond with my hydrogen so here, and my blue electrons are now a lone pair on my oxygen, and that oxygen now has a negative charge because it's lost the hydrogen ion H+. So this is just a little example about how we use curly arrows. You'll do lots of examples of reaction mechanisms as we go through the course and get used to them. But the key thing is a curly arrow can only start from a lone pair of electrons or from a bond, because that's where the electrons are. So that's it for basic concepts in organic chemistry, and the next unit is the alkanes, which you will be looking at your first proper reaction mechanism in that topic. So I hope you found the video useful, and as I say, if you would like to download this as a PDF, you are very welcome to from the website, and log in, and then it will be available for you to download.